I want to show you a couple different ways to think about this, and I have no problem. We could probably even think of a third way to do this. I'll show you at least two of them. And so I'm going to show you, to start off with, I'm going to show you like the very formulaic step 1, step 2, step 3 way of doing it. This is the way you're going to see this in textbooks for sure. So what you would do if you see a composite function, you're going to want to identify the inside part of the composite. So in an example like number 2, what's the inside? 5x. So we would say u is equal to 5x. We're going to set u equal to whatever that inside is. And we're also going to then find the derivative of that inside. So I would say du dx is equal to 5. And then what we typically do is we would mentally multiply the dx over automatically. So instead of writing that, we would probably just write du equals 5 dx. And once we've done that, we can get busy substituting. So I'd go back up to this integral of cosine 5x dx, and I would start substituting all my u stuff. So it would be cosine of u, and the dx would still be there. What could I substitute in for the dx? Not just du, it'd have to be du over 5. I'd take this and I would divide both sides by 5. dx is equal to du over 5. So then I'd get to cosine of u times du over 5. So over 5 is really times 1/5, right? Yes. So this would be 1/5 integral of cosine of u times du. And what's the antiderivative of cosine of u? So our final answer here would be 1/5 sine of u plus c. I guess it's not our final answer. We'd have to back substitute. So it'd be 1/5 sine of 5x plus c. Anyways, very tried and true way, substitution, totally valid thing to do in math. Hopefully that makes a lot of sense, how you can plug things in, do your work, and then re-plug the 5x back in there. How could you test this out to see if this really was the derivative or the antiderivative? Take the derivative of that. Yeah, find the derivative of that, and you'd find that the 5 that comes out from the chain rule would cancel out with the 1/5, and it would all work out really, really nicely. I do have an alternative for these more simple ones, and I can't remember in the video if I talked about Timmy or not. But for a simple one like this, I would use what I call Timmy messed up the chain rule. Timmy is just some fictional character that I made up like 18 years ago, and his name has always just been Timmy. And weirdly enough, over the last like 20 years or so that I've taught calculus, I've only had one Tim in class. So I've only had to deal with the, yes, I'm not talking about you. This is a fictional Timmy that messes up all the time. I've only had one Tim, only one Timmy in the whole deal. Anyway, so here's what you would do. You're doing some of this in your head, but I think it's pretty easy stuff to do in your head. You're going to look at this and say, all right, integral of cosine 5x, and you're going to mentally identify the inside part. And you're going to say, hey, the inside's 5x. And then you say, what's the derivative of that inside? And you would say 5. Then here's the key. Is the other factor in the integrand 5? No. What is it? 1. Technically it's a 1, right? It's 1 times cosine of 5x. So Timmy totally messed it up. He messed the chain rule up. In order for this to be a perfect chain rule, the other factor has to match the derivative of the inside. And so he has messed up. The good news is we can fix his error. Here's what we do. We just go, oh, sorry, Timmy, you messed up. So let's put that 5 in there where it belongs. 5 times cosine of 5x. But of course, you know that you can't just do that and call it good. Like with a math expression like this, if you multiply the inside by 5, you'd better balance it by dividing by 5 or multiplying the outside by 1/5. Yeah. So if I multiply the outside by 1/5, let's think about what we just did. I multiplied the inside by 5 and the outside by 1/5. I multiplied the whole thing by a really strategic 1. So I haven't changed the value. I've simply changed the form. Here's what happens. As I anti-differentiate, the 5 just reverses the chain rule and goes back in where it came from, right? Didn't it come from doing the chain rule? So it just goes back in where it came from. It like disappears, if you will. The 1/5 does not. The only thing we actually anti-differentiate would be cosine. So it'd be 1/5 sine of 5x plus c. So you can see from a space perspective, it's like multiply by a constant, balance it out, done. So I only advocate this for the simple ones where you can like do all this little mental gymnastics real quick, and you can still check these. But from a time perspective, it's way faster. The substitution still is a valid method, and we'll still use that at times. but I think this could be just a quick method, a quick tool in your toolbox that you could get something done fast and move on. Make sense? You could even do this with more complicated ones too, but whatever. So when you hear me talk about Timmy, that's it. So it is what it is. Okay, so let's do some other ones. I'm okay if you just ignore the whole Timmy thing. You're like, that's weird, I don't want to do that. It's fine. It's not going to hurt my feelings, but I know I can do it 10 times faster than you because I'm just going to do Timmy messed up the chain rule. And I would love for you to be fast too. So take a look at number 3, and you decide, do I want to use whatever method I want to use? See if you can execute it. Feel free to check your answer by doing a derivative as well. We'll check your answer, and I'll show you some thoughts here in a second as well. Ready, go. Again, I'll show you both ways here, and I'm going to advocate, I'll show you Timmy messed it up first and show you how fast this could be. Here's what I would do. If I had a little more space, I would just do this in one step. I'll rewrite this real quick. I've got x squared, and maybe we convert this over to a rational exponent like this. Here's what I would do. I'm going to say my thoughts. I would look at the inside and say, what's the derivative of the inside? And I should be replying 3x squared. Is the other factor 3x squared? Timmy, you messed it up. It's only x squared. So good news is he only messed up by a constant multiple. So I can fix his error very easily by just multiplying that by 3. But I have to balance that out by putting a 1/3 here. And here's how this works. The 3x squared is just going to go back where it came from. It's just going to go back inside the composite function. The 1/3 doesn't go anywhere. The only thing I really have to anti-differentiate is the 1/2. So to anti-differentiate 1/2, it's going to be x cubed plus 1 to the 3/2. Of course, divided by 3/2 is really multiplied by 2/3 plus c. And I'm done. No substitution, no du's, no dx's, no u's for that matter. This is why I like this, but I'll show you the u substitution way as well. Brandon.
Can you explain why the 3x squared goes back in?
Sure. So let's let me clean this one up a little bit. And let's check this, and I'll show you where it came from so you know why it goes back in. So if I checked this by doing a derivative, I would say d dx of 2/9 times x cubed plus 1 to the 3/2 plus c. So 2/9 is just a constant multiple, so that's just going to stay where it is. So it's going to be 2/9 times, the power rule would be 3/2 times x cubed plus 1 to the 1/2. Get ready for it. That 3x squared is coming out times 3x squared. So it came from the inside. It came from the derivative of the inside. So when you reverse the derivative, shouldn't it just go back in? Yeah. Just goes back where it came from and like disappears. That's where it's disappearing to. Just going back inside. We're reversing it. It came from the inside, so we're just going to put it back inside where it came from to begin with. Hello. How's it going? Did you need to talk to me? Cool. Well, let me get these guys started on something. You guys good with that part? Yeah. Okay. Do you want? How many of you did substitution on that one? Just kind of curious. Like you did the full on u's and du's and dx's and all that stuff? Okay, that's cool. Did you get the same thing I did?
Yeah. Mm-hmm. But that makes sense. I got confused. I didn't understand the
you do your method. I'll keep trying to pitch this, but you do your method, okay? It's okay. You can do either one. I'm not going to be upset whichever one you choose. Okay, please try number 4. Number 4. Again, if we take a little more of a structured approach to number 4, we would maybe look at this and say, what's the inside function? The inside function is x squared plus 1. And we're always going to set that inside function equal to that. So u equals x squared plus 1. And then just by habit, we always want to find du. So du is equal to 2x times dx. We're just mentally multiplying that dx over there to the other side. And then I am going to start trying to substitute. So let's see here. The u goes right here. And then I still have an x and a dx. What does x times dx equal to? Do you guys substitute differently than I do? I don't know if this is how I usually do it. So I'm just going to divide both sides by 2. So du over 2 is equal to x times dx. So what I can then do is replace the x times the dx with du over 2. I could just substitute for both in one shot. So I would go with u to the negative 1/3 times du. And is it okay if I just mentally pull the 1/2 out? Do you guys do it that way too? I'm trying really hard not to confuse you. I hope that, is this going good? Okay. So then we have a pretty simple power rule for integrals here. So it's going to be 1/2 times negative 1/3 plus 1 would be 2/3. So u to the 2/3 dividing by 2/3, you actually multiply by 3/2 plus c. And then lastly, it would be 3/4. Plug back in, x squared plus 1 to the 2/3 plus c. And you can always check these by doing a derivative and actually doing the chain rule, finding the derivative there, and it should match with your original integrand. How's it going? It's all feeling pretty familiar? Like AB, like we practice this to death, don't we? I mean, like in AB, I feel like we do this over the course of like 3-4 days, and then we just keep doing it later on. And yeah, okay, good deal. Jade and Jeff, how's it going? Doing pretty good? Yeah. Okay, cool.
It's so windy. So no.
Hope that goes away. Okay, example number 5. It's our last one like this. What would you guys do before you thought about any kind of substituting or Timmy stuff? Yeah, bring it up. And by the way, I said this last year plenty of times. I'll say it this year plenty of times too. Antiderivatives of fractions takes a lot of extra attention, doesn't it? It's not simplistic. It takes on all kinds of different forms. And this year we will learn, I think, two more different tools to deal with fractions, I think. I think that's what it is. At least 2 more. Okay, so maybe we rewrite it like this. Antiderivative of x squared times 4 plus x cubed to the negative 5th. Have you guys figured out that these questions have to be really carefully designed to work in a certain way? Like, for instance, what if I wrote, instead of 4 plus x cubed in there, what if it was like 4 plus x to the 6th? You're going to have an issue, right? So these are carefully designed to work in a certain way. See if you guys can work that out, either by substitution or fixing Timmy's problem. And then I'm going to look at the other factor and ask myself, does that other factor match that derivative of the inside? Of course it doesn't. Timmy's off by a factor of 3, kind of like he was before. So thankfully his error is very fixable. I'm simply going to multiply that x squared by 3, creating a perfect chain rule. But I'm not allowed to do that unless I balance that out by multiplying the outside by 1/3 as well. At this point, I'm ready to find my antiderivative. The 1/3 continues on down. The 3x squared simply goes back where it came from and disappears back in there. The only thing I actually have to anti-differentiate is the negative 5th power. So this would be 4 plus x cubed to the negative 4th divided by negative 4 and plus c. So it'd be negative 1/12 times all that plus c. So again, U substitution would work great there. I personally feel like Timmy is pretty fast. That's why I like that. Up to you what you want to do.
Actually, I guess with these U substitutions and Timmy, there's like always an x of a lesser degree.
By 1. Or maybe a trig function that's the derivative of, or some form of the derivative of the whatever the inside was. There has to be some nice matching or like almost matching factor for it to work out like this.
Okay.
Yeah. So like I said before, they're carefully designed. You mess one little thing up. So you guys saw this. We were just discussing this back there. Like I said before, these questions are always carefully designed to work in a certain way so you can practice your skill and recognize patterns and situations. But even if one little tiny thing is messed up, like this one, then it gets really tough really fast. You can only adjust by like a constant multiple of like 5 or -3 or 26. You can't adjust by like x or x squared. If you find yourself saying, hey, if we just multiplied by an x or substituted an extra x in there or something, that means you've either made maybe a mistake or it's completely a different form. And I think that understanding will really help you as we start to work with fractions a little bit more this year. There will be those times you're like, well, only if there was an x there, it would be this. Oh, but it's actually a partial fraction decomp. You remember that?
Yeah.
You want to know the good news about that? You want to know? You want to know, Liz? I do have very good news on that front, though.
There's a calculator program for it?
Do you remember like those horrible words like irreducible quadratic?
No.
Repeated linear.
I feel like I blocked that
if
out.
you did DC, you did that. Listen, when we get to those, listen please. When we get to those, we will do the simplest conceivable versions of that. We're not going to get into all that really nasty stuff. They're the simplest version, and I think the fears you might be feeling right now, you'll be like, oh, that's all? Okay. Like, seriously, I've heard this chorus before of like partial fractions, and then we get to them and they're like, oh, that's it? I'm like, yeah, that's it. And they're like, oh, okay. That's not that bad. So Liz, I hope that's the tune you're singing later. So guys, the bottom line with this one is very simple. We can't do this one with the techniques that we've learned so far. We would not, like this would be a poorly written question for our purposes, so we're not going to do this one. We can't use any of our techniques to do this. Right now, you will learn a technique later on that would sort of kind of deal with it, but not at the moment. Okay, the intro video did keep going on here with some U substitution. So there is one of these two where U substitution is mandatory, and the other one where it is kind of optional, but I think still quite useful. The first example, the one there, number 2, U substitution on that one is completely mandatory. You have to use it. The second one, number 3, with all the cosines and sines and all that stuff, I think that U substitution is quite helpful, but it's not mandatory. You still could do the whole Timmy thing. I tend to do U substitution with that one. So if you guys would, please try numbers 2 and 3. And maybe, I don't know which one you'd want to try first. They both have their challenges. Let's see what you can do.
You were saying you can't do anything for number 2?
No. Because what you would do is you'd say the inside is 2x minus 1. 2, when you say is the other factor of 2, no, it's an x. And so you're like, the pattern's wrong, right? You can't adjust by an x. You can totally change the form of it. So that's one where that one just kind of, one of the exceptions to the rule where you could use that. And that's why I say, like, knowing U substitution is great, and I think something you should know.
Yeah.
But if you can use the whole Timmy thing to get through the easy ones quickly, you spend like 3 minutes on it instead of 4 of them, instead of like 10 minutes on it, you just save yourself time. So to me, that's the reason for thinking about that. Okay, we're looking at examples 2 and 3, seeing what we can do with these. They're both tougher for sure. See how it goes. So guys, number 2, this one was probably walking around probably the trickiest for you. This would start off very normal as far as substitution goes. You would say that the inside expression is the U, so I'd go U equals 2x minus 1. Then du naturally would be 2 dx. And then I'd start substituting, and when I do that, I would get the integral, the antiderivative of x times u to the 1/2, and then it would be du over 2 when I substitute in for the dx. So far, does that make sense? Yeah. I haven't finished my substitution yet because obviously there's still an x in there. That's okay. So this next step, I think there's 2 challenging steps in here. I think the next step is probably the more challenging of the 2. Basically, it's this. How do I get rid of that x and replace it with something that has a u? Anybody, can you give voice? Can you express how you do that? I know some of you know. What do? I got to get it out of there and replace it with a u expression.
Solve it.
Solve what?
Solve 4x.
Solve. This is the only relationship I have between u and x. So, if I take this and I add 1 and divide by 2 on both sides, I get u plus 1 over 2 equals x. So I can tell that was maybe the key for some of you. Good? So then maybe the next step would be 1/2 integral of u plus 1 all over 2 times u to the 1/2 du. We're still not out of this yet. Are you guys okay with this over 2 really being a 1/2 factor?
Yep.
Which I'm just going to get out of there. So it'd be 1/4, leaving me with u plus 1 times u to the 1/2 du. And we finally get to the last crux of this, the last real significant challenge. It's easy to look at this and feel like you've done a lot of work, you've done a lot of heavy lifting, and yay, I'm ready to just finish this off. But it's a product. And integrands that are products are notoriously difficult and complicated, and we'd rather avoid them if we can, and we really need to avoid it here. So how could I take that integrand and take it from being a product to not being a product? Distributive property. So Jasmine has the perfect hand motion, perfect rainbows, distributive rainbows. So this gives us 1/4 integral of u to the 3/2 plus u to the 1/2 du. And now finally we have a nice sum in there and we're ready to find an antiderivative. So I try to come up here and we'll get this worked in. So it'd be 1/4 times, I guess it'd be 2/5 u to the 5/2 plus 2/3 u to the 3/2 quantity plus c. And then all I got to do now is plug back in. I'll distribute the 1/4 too. So I guess it'd be 1/10 times 2x minus 1 to the 5/2 plus 1/6 2x minus 1 to the 3/2 plus c. So that's a pretty complicated one. I have yet to see one of those show up on an AP test. I don't get to see all the multiple choice, but I haven't seen one of those yet. Figure if you can do that, then hopefully the AP test will go pretty well. Yes, sir. Yes, sir. And then the other one here. Darn it. Hey, listen up. Listen up, please. Hey, listen up. I just realized the analogy that I use is going to make sense to about half of you. When I teach the chain rule, I teach it with boxes. Do you guys remember that? Yes. So that's right. You open up the present. We just got done with this in AB, actually. So I would look at this, clearly very composite here, right? A lot of stuff inside other stuff, very composite, like we've been doing this whole class. If you look at this, this is kind of the main part of the composite, right? Because it's a 3x has been put into sine, and then that whole thing has been put into the square it function, or the squared function. And so when it comes to time over here to say, hey, let's go ahead and substitute here, let's find a u and a du and all that stuff, you really have a choice. You could say that the inside function is 3x. That would be perfectly reasonable to do, wouldn't it? Or couldn't you say that the inside function is sine of 3x? The only thing you couldn't call the inside would be the squared function. That's the outside one. So as far as like the boxes or the inside outside, like would you want to put, like, what do you think is better? Because it would work either way. What do you think is better? The 3x, like the little tiny box for the u, or the medium box for the u? Medium is better. The one in the middle is better. So I am going to say u equals sine of 3x, picking the medium-sized box, so the middle function, I guess, maybe would be another way to say it. Therefore, what would du have to be?
3 cosine of 3x.
Good job. 3 cosine of 3x dx. So here's our substitution. I'm going to replace sine of 3x with u. So it would just be u squared. I still have cosine of 3x, and I still have dx. What could I replace the dx with? Yeah, that whole big expression, it would be u squared times cosine 3x times du over 3 cosine of 3x. As I do a little bit of division and substituting here, wouldn't this then cancel with that?
Yeah.
It's kind of the whole point. Giving us 1/3 integral u squared du. And you got to admit, even if you like the whole Timmy messed up the chain rule thing, which I do, you got to admit, using substitution to go from this to this, makes for a much more pleasant experience on the whole anti-differentiating thing. Makes a big difference, I think. So then here, just use a simple power rule. You get 1/9 u cubed plus c. And you get up here 1/9 sine of 3x quantity cubed plus c. Should be able to differentiate it to check it. I think it would work out nicely. Okay. Any questions at all? So let me decide what I want to do.
I don't think we ever introduced ourselves. I feel like it's really just doing that as you get older. And then you just get
Let's do this.
you know each other and you don't. Yeah. It's so awkward. I don't know.
As we're going to do this final page, we'll come back to that change of variable. We'll do that on Monday. This is going to work out really nicely. I think on Monday we'll be able to do everything we need to do, and might even have a few extra minutes left over, which is, as you know, a rare thing. Okay, so from pre-calc, you guys remember evens and odds?
I just remember because I never knew what it was when it was on me. Being honest, I blocked out most of pre-calc from my memory subconsciously.
Well, we'll get the stuff we need.
Okay.
We'll get just that. There are lots of really interesting characteristics of evens and odds. We are going to focus on the things that we need to focus on. Even functions are symmetric with respect to what? The y-axis. That is correct. So a nice example is f of x equals negative x squared plus 4. That is a parabola opening down, shifted up 4. And so it would look about like this. It's a little lopsided, but okay. All right, so then if we found the integral from negative 1 to 1 of f of x equals the integral from negative 1 to 1 of f of x, which is 22 thirds, what would the integral from 0 to 1 be? Based on the graph, wouldn't it have to be half that? So 11 thirds. So we're basically saying the area from here to here is 22 thirds. Therefore, the area over half the interval would have to be half the area, 11 thirds, or 22/6, if you will. General principle is if f is an even function, then the integral from negative a to a would be double the integral from 0 to a, and all the other variations that you could write based on that. I think the graph is very helpful to see. Did you guys also know some of the trig functions, or at least one of the trig functions is even? You guys know which trig function is an even function? It's cosine. Cosine. Yeah, so yeah, if you think about the graph of cosine, it does something like that. You say doink point? Yeah. There's no doink points on cosine. All right. I will reveal something about that here in a second. Okay, then let's look at the odd functions too. Sorry, excuse me.
Sorry.
Work my way through this rough crowd. Pretty intimidating looking crowd here. I'll just go the other way.
Who said that? Who said what?
Hey, I got something to leave you with, I think, that'll make you... Hey, listen, stop talking. This will make you think a little bit this weekend. Odd functions are symmetric with respect to the origin. And so there are lots of odd functions. The classic one is the cubic, right? Y equals x cubed. I choose not to use that one. I choose to use sine. So sine looks... that's one of my better sine functions. I feel pretty good about that one. So based on a graph like that with that origin symmetry, if the integral from 0 to pi was 2, which it actually is, then what do you guys think the integral from negative pi to pi would be? 0. It would have to be 0 because, of course, the area over here would be the exact same as the other area, but it would be below the x-axis. So it would accumulate negatives instead of positives, and they'd essentially add each other out. General principle here, if g is odd, then the integral from negative a to a, if you have a symmetric limits there, you'll get 0. Where I want to leave you guys with here in a second is this. You guys remember the rule for odd functions in regards to their exponents? They're odds, yeah. So if you saw something like this, f of x equals x to the fifth plus 4x cubed minus x, that would have to be an odd function, right?
Do they all have to be odd?
All of them.
They can't just be like x to the fifth plus x to the fourth?
All of them have to be odd. Yep.
What?
What if it was 4x squared? Or do all the exponents have
All of them have to be odd. Hey guys, hey, listen up. I know you're excited. I know we're going to go here in like 2 minutes. So that is kind of a general principle with odd functions. So the question I would leave you with, and I will sort of reveal the answer here to you, is if that's the case, how does sine fit with this? Like, why would sine be odd? I mean, I realize it's sine to the first, but it's also cosine to the first, and that's even. So that doesn't really work.
I remember this. You and I talked about this at one point, didn't we?
We might have. We very well could have. So,
Because sine can be written as.
let me just leave you with a little tease for later on this year. Later on, you are going to learn this. Please just watch. You're going to learn this, that sine of x can be written in a form that looks totally different. So if you start that pattern, and the dot, dot, dot means just keep on going with it, right? So if you were to take that pattern off to just keep going and going and going, you would not end up with something that is close to sine. You would end up with exactly sine. Exactly. And that's where we'll go in the second semester, but that's obviously like 3 months away. So we'll get there when we get there. See you guys. Have a great weekend. You guys want to say hi to Alexandra?
Hi, Alexandra.
All right. Thank you. See you guys.